So what Danielle did is she sent me 4 questions that she thought were typical. Well, I guess you actually got these questions from some of the researchers here, but she thought they were general enough that it was worthwhile my coming and trying to give an answer to them here to a group of people. So what I've done is probably put together quite a long answer to some of these, trying to go a little bit beyond what the question might have been. But if you've got more questions about the question, don't hesitate to ask. And I don't know, should they use the microphone if they want to do that? No, it will pick up, will it, if they ask a question? Okay.
If somebody has a question, they'll answer this way, that would be the microphone. And it's not for the audience, it's for those who are watching on internet.
Yes, okay. Okay, great. That's what we'll do then. And after 2 questions, after question number 2, we'll take a break. Okay, good. Okay. So let's see here. So I actually put up a question 0 just to tell a little bit more about what is the Data Analysis Resource Center that I come from. Now, I've also been told I'm not supposed to move very far, so if I kind of jiggle around. I'm sorry about that, because I usually walk when I'm talking. I usually walk a little more. So let's see how this works. So the Data Analysis Resource Center is just a very small group at Statistics Canada, probably the equivalent of 4 or 5 people. That's all we have. We're all methodologists, and we specialize in analytical methods and also analytical software. That's what we do most of the time. And some of us in the group don't even do that all the time. So we're quite small. But what we're trying to do is to encourage, suggest, and provide good analytical methods and tools for use with StatCan data. And most of the time, we concentrate on survey data, although we sometimes work with people on other types of data too. And how we get around to our encouraging, suggesting, and providing is we do consultations. We're consulting with the analysts at Statistics Canada. We're consulting with the analysts in the research data centers. Sometimes we do some direct consultations with the researchers here in the RDCs. We certainly consult and collaborate with other methodologists because in our group, we're not attached to any of the particular surveys. So we often go to the methodologists with questions about their surveys, and they come to us with questions about some possible analytical methods. And then we do teach some courses. We do evaluation of technical papers, and we do a variety of other things too as part of DARC. But we are there for people to consult with. So the researchers here can definitely get in touch with us if they want to. Now, so let's just go on to the first question I got. And the question was, what's the position of StatCan on accounting for the impact of survey design when fitting multi-level models to complex survey data? As you know, multi-level modeling or hierarchical modeling has become very popular as a method of analysis. So how are they supposed to do that if you're working with survey data? Well, the quick answer, we don't really have a position on that or any policy on any particular, on multi-level modeling or any other type of analysis. And if you went into our data analysis and presentation chapter in the Statistics Canada Quality Guidelines, it's not very specific in its recommendations either. Now, I should mention, the Statistics Canada Quality Guidelines, which are for all different aspects of a survey, are now a new version is now on our website, and it's an interesting little document to look at if you're doing analysis or if you're carrying out a survey. Lots of good pointers. The chapter on data analysis and presentation just goes through a lot of different points that if you're doing an analytical paper may twig to things that you should consider, particularly if you're thinking of putting that paper in a StatCan publication. So, but here are a couple of excerpts from the quality guidelines. It says choose an analytical approach that's appropriate to the question being investigated and the data to be analyzed. So, appropriate. Or assess whether the survey design information can be incorporated into the analysis, and if so, how should this be done? Such as, could you use a design-based approach? Now the question was, is there a design-based approach if what you're wanting to do is hierarchical modeling? Well, the short answer is, it depends on what you're interested in measuring as to whether we really have a design-based method for this yet. So what I'm going to assume is that if someone says they want to do multi-level modeling, that what their focus is the parameters in that model. So they're interested in the parameters associated with the random effects and also the parameters associated with the fixed part of the model. So their main focus is to be able to estimate those parameters, get variance estimates for those parameters, and then use those estimates and the variance estimates for doing some sort of inference with that model. Well, do we have a design-based method for this? Well, really, multi-level modeling of survey data is really still an area of research, and there is a little bit of research going on at StatCan. There's quite a bit of research going on with people in the United States. But that being said, most of the statistical research where we've got papers on it, they're still restricted to the particular case where the hierarchical structure of the model matches the hierarchical structure of the survey design. So if you were interested in fitting a hierarchical model to children within schools, within school districts, then you would have to actually have a survey design that matched that picked school districts, then picked schools, and picked children to make use of the results of this statistical research. One nice thing, though, is that several commercial packages have actually implemented the research results for this particular case of where the structure of the model matches the structure of the design. One thing I forgot to do is bring a list of the references. There's a little paper by Shantala and Sukandran, which is, and I did find out it was 2006. I forgot to take the question mark out. And it's in the Proceedings of the Joint Statistical Methods, where they've actually gone and looked at several of the commercial packages that say they do hierarchical modeling and checked out what they do for this particular case, and do the results actually match up amongst the different software. So it's an interesting little paper to read. It's quite readable. So what I'll do, Danielle, I will send you a list of the references after. I'm sorry I forgot to include them. So the question then would be, are there any problems with using these software with StatCan survey data? And as I said before, you need to have the hierarchical structure of your model and your design to be the same. And we really don't have that many cases of that with our StatCan surveys for the cases that people are wanting to fit hierarchical models. Another thing is you do need to have weights for each level of your model. And as you know, most of the StatCan surveys just have one weight on them, or at one level. It's usually a person weight. So it wouldn't have, if you were doing persons within schools, within school districts, StatCan at the moment would still just have a person weight on the data file. And a third problem is that this, we do have software that will fit this hierarchical structure, but they only provide design-based variance estimates in a Taylor approach, so they can't use the bootstrap weights, which we have for most of our surveys. So there are some problems at the moment. But we do have some special cases where the model and design do coincide, and they do happen to match some of the research that people are doing. For example, we have the occasional survey where we do have multi-levels, and we actually provide weights at the different levels. One of these is the Workplace and Employee Survey, which is WES that goes by. The design of the survey is we pick businesses, and then we pick employees within the businesses. And that's often the type of multi-level model that people are wanting to use. And another situation is where we have people and then the times within people. What people are then, the researchers want is a two-level growth model. So both of those cases seem to fit in to the situation where the model and the design coincide enough that you could use these methods. And actually, for both of these cases, weights do exist for both of the levels. For example, for the West survey, we actually provide the weights. We've got business weights, we've got employee weights. For simple growth model, where all you have is the two levels, person level, and then you've got the times within a person, like maybe every 2 years if you're if that's where you have your data. Well, you've got a person level weight on the file, and generally the time weight could actually be taken to be 1 because there's no sampling of times. The times that have been chosen for the design are every 2 years, and every person is supposed to give an answer at every one of those years. So the probability of a time being selected, given that a person is selected, is 1. So you could use a weight of 1 as your weight for that other level. So here are two situations where you could use that research that has been done. Now, both of those cases have bootstrap weights and want you to use those for your design-based variance estimation. Well, but the software now doesn't really accommodate that, the commercial software. So actually within my group, a couple of the people, neither of whom are still in the group, Fritz Pierre and Nasser Saidi, wrote a little SAS macro, which they then use with the HLM package, the hierarchical linear modeling package. And what they were doing is they were able to loop back and forth with the bootstrap weights and use HLM for doing the estimation of all the parameters, and then as I say, do the looping with the bootstrap weights and then produce variance estimates. That software is available for anyone who wants to use it, and I could get it and give access to it to anyone. Another thing that is perhaps close to being available is something in M+. The developers of M+ have said that they are actually working on being able to use replication weights in their multi-level modeling software. And so they've actually been in touch with us to ask whether we could try it out once they've got a beta version. And we're expecting that any day, so hopefully it works well. And they were actually, they'd seen some of the papers that our group had produced, and there was also a paper produced by a researcher in the United States, Laura Stapleton. So on the M+ website, you see a reference to Laura Stapleton's paper. as the impetus for them going to some of the replication methods. I guess then do you actually have any other options if neither of those seem a possibility to you? Well, you still could go back and do a model-based approach, because we have lots of really good software for multi-level models. But what you're going to have to do is try to learn enough about the survey design that you could include any effects from the design directly in your model. Because often for a survey, why we do a design-based approach is because we don't have enough knowledge about the survey to model it directly, or we really don't want to bother doing that. But since we are limited in what we can do with software for multi-level modeling for survey data, here's another option. And if you take that option, or actually if you take any option, if you use some of the little macros I talk about, make sure you describe the approach in your paper and telling what exactly you're doing. If you're taking a model-based approach, say you're not using the survey weights, you're not using anything about the bootstrap weights or strata and clusters directly in a design-based manner in your paper, so that other people know what you've done. And also it gives a record for when we do have approaches which we feel are better. Perhaps someone can go back and redo those particular cases and see if you actually come out with different conclusions from your analysis. So that's about all I can offer on that particular topic. I know that multi-level modeling is quite popular. And I think NLSCY is one survey where that's particularly the case. Is anyone here doing it? No? Yeah? With which survey?
The National Population Health Survey, also the
Canadian Community Health Survey?
Yes,
Yeah.
I'm working with these two surveys and encountered a lot of problems
Yes.
when trying to implement some multi-level modeling with these data.
Yes. We're hoping we'll have a better answer sometime soon. Yeah. Anyway, so that's the first question that Danielle sent to me. Here's another question. Is it possible to combine cycles 1.1, 2.1, 3.1, 4, in the question said 4.1 and 5.1 of the Canadian Community Health Survey? I actually couldn't find anything that called it 5.1. So I think what they were asking was the 2007 data file and the 2008 data file. And is it possible to combine them, and what would be an appropriate way to do it? So that was the question. And there was a little bit more. I think the person was interested in, had a research project related to mammography, and I think they were also interested in possibly doing their research just within Montreal, or the Montreal Health Region, which makes me think that one of the reasons why they're wanting to combine cycles might be because they might be wanting to look at a special subpopulation of women, and they want then to get a bigger sample size by getting people from several cycles. But I'm not sure whether that's actually the main reason for the question or not. So this is a question that comes up quite often. And my quick answer is actually going to be the answer to many of the questions. It really depends on the sorts of parameters that the researcher is wanting to measure. And it's going to also depend on the particular data sources that the researcher wants to combine. Now this here, it's going to be what of those, do you actually want to combine all 5 of those data sources, or are you perhaps just interested in combining the first 2 or 3 in whatever the analysis is? So what I want to do is, from the questions we've had from various people, mostly from the research data centers, is I'm just going to tell you about the different type of estimates people seem to want to do when they're thinking of combining. Now, I'm going to divide them up into 3 different types, 2 of which I'm going to call different types of descriptive, and then sort of an analytical type. So in the descriptive type, first of all, what they're wanting to do overall, they want to estimate some characteristics of one or more finite populations. As you know, every survey is collecting data about one particular finite population, or that's how Statistics Canada presents the data. The researcher himself may be looking beyond that finite population, but often they're not. They want to estimate the characteristics of the various finite populations that are in those different data sets. And the sorts of characteristics they might want to estimate would, I've actually broken down as some possibilities here. They might actually want to take the average of some characteristic in the different populations. For example, if you've just got 2 populations, what they may want is a weighted average of some sort of proportion. Say, the proportion of women that have had a mammography, a mammogram, I mean. So they want a weighted estimate of those 2 proportions from one population and the other one. And really, we're making no assumption that the rates are the same in the 2 time points, but an average, a weighted average, is still of interest to them. Another possibility would be a rate for combined target populations. Like you actually are willing to put together the 2 populations from your 2 different data sources, and you want a rate over that. So it might be like the rate of mammography for the combined female populations of 2001 and 2003. Now, this might sound kind of odd to you, but or to try and come up with an example, but one example I was thinking of on the train this morning was, this probably comes up, say if someone were studying the people that were coming to a mission, homeless people coming to a mission to stay overnight, and what the administrator there might want to give some statistics on how many beds were filled, I guess you could say, over Saturday and Friday night, or Saturday and Sunday night, say. So they're not, if the same person comes both nights, they're going to count them as 2 different people. It's really how many visits are there. So this is the same sort of thing where you actually want the combination of the people from 2 populations. The same people could be part of both of those populations, though. And then you may actually be, another thing you might be interested in is a difference in rates between 2 of the populations. So something like this. So say the change between 2001 and 2003 mammography rates. So these are the sort of descriptive things, not making any sort of assumption about what the rates are at the different points, like not making any assumptions that the rates are the same at all, but descriptive statistics like that. Another type of estimate is usually descriptive still, but we actually assume some sort of relationship, such as, and this is often what you'll see people do. They want, say, for example, the rate over the combined populations, but they want to make the assumption that each population has the same rate. So example, percentage of females who had a mammography in 2001, 2003, or 2005, where the rate is assumed to be the same in all 3 years. So that might be something they'd want to estimate. Or they may want the rate at a midpoint in time among sampled populations, where you're actually going to assume some relationship of those rates over time, say. So we've got this type of descriptive thing, and they want estimates for those. Or the third kind is what we often see is what we're calling analytic, and that would be we're wanting to estimate relationships thought to hold beyond those specific finite populations, and people often want to do this by using a model. So, for example, using the mammography thing, maybe someone would be interested in estimating the odds of having a mammogram for poor women compared to rich women, controlling for the effect of age, education, and race, using a logistic model, and they want to use the data from more than one time point for that, from more than one of these CCHS samples. So these are the types of various types of estimates people may want to make. Well, how to decide on how the methodology you should use for combining those? Often what you can do is if you look at the different randomization frameworks, that's going to give you strong guidance on how you could proceed to estimate your quantities and then to make inferences about them. So it's to estimate them, to estimate their variance, and then do your hypothesis tests. And why I say let's look at the different randomization frameworks is, you know, when we're taking data from a sample or from a survey, we only have one of the possible samples that could have been obtained from the particular survey designs. So you know what you've observed, but you also, depending on the randomization framework that you're putting in place, you also have some idea of what you could have observed. So, and what you think could have observed is going to affect how you estimate your quantities, how you estimate their variance. So here's one possibility where it's a particular randomization framework, and the descriptive approach, or the estimation approach, I'm going to call the separate approach. Because what we have, suppose we're trying to combine two different populations, two different CCHS samples, say. So here we have the first one, and there's a finite target population behind that survey. There's some sampling process. That sampling process could have given us any number of different samples, and here's the one that we actually got. Then we've got the second survey. It had a finite target population behind it, a sampling process, different samples that could have been obtained, and here's the one that we actually got. Now, in the separate approach, what you're trying to estimate actually can be expressed as some combination of the parameters from this population and this population. So you estimate the parameter from this population just using that sample, and there it is. Then you estimate whatever that parameter is from the second population just from that sample, and there it is. And then you combine this estimate with this estimate to come up with the overall estimate, depending on what was the relationship between the actual quantities you're interested in. For example, if the quantity you were interested in was alpha times the proportion from the first population plus 1 minus alpha times the proportion from the second population, you could estimate the proportion from the first population by this, estimate the proportion from the second population by this, and then you go alpha theta hat 1 times 1 minus alpha theta hat 2 to come up with the estimate of the quantity you're interested in. So in the separate approach, you actually work with the two samples independently first, get estimates, and then combine them however you need to. Now, a second possibility is what, for descriptive estimation, is what's called the pooled approach. And this is an approach that a lot of people always are really thinking about taking when they say, can I combine the estimate? So in this one, again, you've got your finite target population and everything's the same. You come down to having a sample that you chose, second one, sample that you chose. And then what you do in some way or other, you pool those two samples together to come up with a combined sample. And from that combined sample, you estimate the quantity you're interested in. You essentially, and you often treat this single sample as if it came from one population. And this often is more the approach you take if what you've done is you've made some assumptions about how the parameters are between the two different populations. If you've already assumed that, say, the proportion of women that have mammographies is the same from this population and this population, it may seem reasonable to pool your two samples first of all, come up with a pooled sample to get that common, to estimate the common proportion. And that's often where a pooled approach makes sense. Now here's an even more complex situation, and this is more when we have an analytic study. And remember, often when we have an analytic study, we feel that the relationships that we're interested in actually are true beyond those finite populations that we've sampled. Like if you're looking at the risk factors for diabetes using, say, CCHS, you really feel that if you find risk factors in the CCHS sample for one particular year, you can say that those results probably hold beyond that one finite population. So, and that's the case with a lot of the models that people fit to our data. So in that sort of situation, what people are thinking is that we have actually an infinite target population, which is made up of all different finite populations. So, and from that infinite target population, we actually could have a whole bunch of finite populations. Here's one, here's one, here's one, and here's the one that we actually had. And that's the one from which we took our sample. And maybe from the same infinite target population, we got the second finite population from which we took our sample. So maybe this is CCHS 1.1, CCHS 2.1. And we take a sample from each. And then we somehow combine, make use of those samples somehow to come up with a combined estimate of whatever we're interested in. And often we do that by pooling these two samples in the same way. So often when an analytic study, it makes sense to take a pooled approach. So just to reiterate, I think this is what people think when they're talking about a pooled approach. So they pool the data from the different surveys into a single file, and then they create a weight variable that's appropriate for the pooled data, for their target population, their assumptions, and the quantities that they're interested in. So sometimes, in many cases, you just use the weight variable that are on the separate files, but there may be cases when you might want to modify that. So you have a weight variable. You then also have to have design information for variance estimation. So, and if you've got bootstrap weights on the separate files, and if you have modified the weight variable, then you'd also have to modify your bootstrap weights. Then probably what you do is you do some confirmatory work about the assumptions that you're making. Things like if what you're making the assumption that, say, the proportion of people with a certain characteristic is the same in different populations, you may want to do some confirmatory work before you actually pool. And then you carry out your estimation and inference on your pooled data, and you're using techniques that would be appropriate for data from a single sample. I think that's what people want to do. They want to treat their data as if it comes from a single sample. So that's what we mean by pooling. And so what I want to, I'll just make a couple more comments here. It is possible to estimate the same quantity by separate and pooled approaches, like particularly descriptive things. But the estimates themselves may not actually be the same. They're estimating the same quantity, but the estimates themselves aren't the same. One may be more efficient than the other. As I've mentioned before, using a pooled approach when fitting models seems like the most reasonable way to proceed. But you shouldn't lose sight of where your data came from. You really should, in your model, look at or include some variables that would account for differences between target populations of the different data sources. And check with, include them first of all, and then see whether they actually need to be there or not. Maybe do some statistical tests to decide whether or not you could drop them. Like, so here's just a very little example where suppose we actually have 3 different samples, and they're different colors here, white, yellow, and green. And what the analyst has read in the literature that there's a linear relationship between 2 variables that they're studying, and they're starting up with their analysis. So they pooled their data and they fit a straight line to the data, and this is what they get. Well, if they had actually thought, well, I know it's a straight line relationship, but I don't know whether that line should actually be the same from my 3 data sources. Let's at least, as an initial start, allow the slope and the intercept to be different for my 2 data sources, or 3 data sources. If they did that, they would actually see that the relationship is of this form, definitely linear, but even the sign of the slope is different. So if they had just gone with this and not included, allowed for different intercepts or slopes, they would have probably been making quite wrong conclusions here. This would be more the situation. Now, sometimes allowing, now it could be that the 3 populations are actually different, but allowing for these different, say, slopes and intercepts where you actually expect them to be the same is always a good idea, because it could be that the underlying populations actually have that, but there's something about the data from your 3 sources that is screwing up what the true relationship should be. So it's always good to do something like this. Now, as I said, okay, we've got all this sort of pooling, what are you estimating, but there's still a whole lot of work you should do first before you actually bring your data together. And a lot of this is going to have to go into the user guide and all the information that you can find out on the survey. For example, are the survey designs the same or very similar? Because different survey designs can have an impact on how people respond. Are the questions and the questionnaires the same? Again, just modifying a question or even modifying where it is in the questionnaire can affect how people respond to it. Is the mode of delivery the same? Like people may answer a question differently if you ask them on the telephone than if you talk to them face to face. For example, if someone asks you over the telephone, how much do you weigh? You can you can say anything, well, but if you're standing in front of that person, you probably have to be more truthful. Is the type of respondent the same? And another thing, are the samples independent? Now, independence of the samples is more for when you get into variance estimation. How do you do it if you're combining two samples where you do have some dependence? And another thing too, I just brought out here, how do the target populations of the data sources compare? Because when I go on to the StatCan website, and there's, I don't know if people have gone to it's called the Integrated Meta Database, but it's from the StatCan website. You can go in and get information on each different survey. And the very first thing they always say about the survey is the target population. And so they'll say the target population of CCHS 3.1 is all people 15 and over in households in Canada. Well, actually, that's not quite true. It's all people in the households in Canada at the time that the survey was carried out. So a target population really has both a target group and a time. So, and this could even if the target groups are the same, the fact that the times are quite different can have an impact on what people would even respond to a particular question. Same target group but different times, and this is actually the most common case, and a different target group and time. Sometimes people do actually want to combine those things. So you have to really think of questions like that to say, do I really have data that I can bring together? And are my assumptions that as characteristics are the same amongst these, would they be true? Because those assumptions will affect how you do your analysis, what the estimates would look like. So, so let's get back to what this person asked. He was saying he wanted to combine cycle 1.1, 2.1, and 3.1 of the CCHS, and these were at 2-year intervals, 2001, 2003, 2005. And then we have, it actually says on the documentation, cycle 4.1, which is actually data collected in 2007 for the CCHS. And then there's also a data file for 2008. Now, over time, for all these 5 different time points, the same target group, if you go on and see the description, the very same target group, but we have different times. And the survey designs have quite a few things in common. Well, each target group is sampled and interviewed just once. That's because these are cross-sectional surveys. But the survey designs are fairly constant for these 3. But starting with these 2, the data are actually collected under a slightly different design. They've gone to what they call continuous sampling, and actually every 2 months of data, even within a year, has been selected so that, or the design for every 2 months is supposed to be representative of each health region. So there are some differences here. And also within each of these years, the sample size is about half of what it was for these 3. So you have to be careful when you actually want to combine. I say in general, if you for combining surveys, variance estimation can be hard if the samples are not independently selected. Well, the cycles 1.1, 2.1, and 3.1 of CCHS can be assumed to be independent. They're not quite, but it's close enough. I said here, I think that the combined 2007-2008 data can be assumed independent of these 3 cycles. I've put in a phone call to the methodologists and just to be sure of that, but I didn't get an answer back. I can follow up on that. Now, as I say, pooling of CCHS data is something that a lot of people wanted to do. So there's actually a paper in the 2009 health reports by Steve Thomas and Brenda Wannell, so where it discusses the combining of data over the first 3 cycles. And I on the website, I found out that they have, for the new 2007-2008, there is a little article saying interpreting estimates from the redesigned Canadian Community Health Survey. And essentially it says we're looking at whether there's any problems of pooling. Further studies are planned, but I don't think they've actually published anything. They do mention that the mode effects could be different in those 2 new cycles than in the last stuff, because they did find CCHS has always been a combination of telephone and personal interviewing, and they have found that the responses from the telephone people have been different from the responses from what we call an area frame. So over the first 3 cycles, what they always tried to do is have the same amount of telephoning, or the same proportion of telephone interviews over the 3 times. Think that they could deal with the problem that way. But I think there's probably needing to be a bit more study here. And as I say, I'll see if they've actually been able to find anything out or not at this point. So, do we want to take a break here? You invited everyone for lunch, Danielle. Okay. And we'll come back in, what, 15 minutes, 20 minutes? Now, the last 2 questions that Danielle sent me both apply to the National Longitudinal Survey of Children and Youth. Are there any people here that are using that survey or have tried to use it? Yeah. Okay. It seems it actually raises a whole lot of questions over time. So what I thought I should do is, first of all, before I even give you the questions, I'm going to look at what the survey looks like. Because what I think a lot of people have trouble with is they maybe not be quite sure of how the survey was designed, and they're very influenced by how the data are arranged, and they really have troubles with doing their analysis because of the arrangement of the data and the fact that in order to do what they want to do, they really need to do a lot of data, just modification of what the data sets are. So here is the design of the NLSCY. It's actually a series of panel surveys, or sometimes we could call them a series of cohorts. And each cohort has a different target group and starts at a different time. So the first cohort, who were all aged 0 to 11 when selected, which was around the start of 1994, they've been followed every 2 years and so on. So this cohort, aged 0 to 11 when selected, and then we're following them over all these different years. Second cohort was aged 0 to 1 when selected, and it was selected around the start of 1996. And actually, it's only being followed for, I guess it's 5 or 6 years. Actually, we only went back to them 3 different times: 96, 97, 98, 99, and 2000, 2001. Third cohort, again, aged 0 to 1, but it was selected at a different time point, and again, it was just followed 3 times. Cohort number 4, aged 0 to 1 when selected, around 2000. and then I think it's sampled 3 times. And then we've got another cohort number 5 and a cohort number 6 and so on, as you know. So we actually have a series of samples, each of which starts at a different time and is followed over time. And all of them are age 0 to 1, except the first one, which is age 0 to 11. And it's this is the one that's being followed for the longest period of time. So that's one picture of the survey. Here's the other view that I think most people see when you go on to the go into the NLSCY literature, where what they tell you is in cycle 1 we have an original cohort that's 0 to 11. At 1996 we have that original cohort, which is 2 to 13 now, and another cohort that's 0 to 1. Cycle 3, we've brought in another new cohort, and then we've got this one, now 2 to 3, this one, now 4 to 15, and so on. And we actually can see here at the time of cycle 5, or in 2002, this cohort, which had been followed for 3 times, isn't followed. And in 2004, this one's not followed, nor is this one. Now in 2006, they actually bring this one back again. The children are now 8 and 9 years old. And in each case, we're following the first big one. And cycle 8, we've got a whole lot of different ones that are not being followed. This one, and this one. And as you know, if you've ever used the NLSCY data, the data are stored by cycle. So you have the data from all these people in cycle 2 files, the data from these people for this time point in another set of data files, all these data for this time point in another set. And so we actually have several different sets of data. And sometimes people get confused about that when they actually start to analyze it. So here is one of the questions that came in. Someone wanted to do an analysis. They want to estimate and compare the proportions of Canadian children aged 2 to 9 in 1994, 1996, 1998, and 2000 who are hyperactive. So they wanted the proportion who are hyperactive at each of those time points. And they also wanted an estimate of the proportion of how many children 2 to 9 are taking Ritalin. I think there was some more there, but this is good enough. So the question is, what weight would you use for doing this analysis? And how is the dependence in the observations accounted for when doing variance estimation? So those 2 questions. Now, I want to go back to what the analyst seems to be asking. He seems to be interested in some characteristics of all Canadians aged 2 to 9 in 1994, then of all Canadians aged 2 to 9 in 1996, of all Canadians aged 2 to 9 in 1998, and of all Canadians aged 2 to 9 in 2000. And he then wants to compare across these populations. So if he were setting up a survey to do this, the ideal survey design would have been to actually have a set of cross-sectional samples. And he'd draw one from the Canadian population at each of those years. And he'd ask them whether they're hyperactive and whatever. That would be the ideal. Well, we do have, if I go back, let me see if I can. We do have a sample of 2 to 9s drawn from the 1994 Canadian population. Let me see, just a second. I'll go back to the picture. Okay, so we do have a sample of 2 to 9-year-olds in 1994, chosen from the 1994 population. When we go to 1996, We do have information on people who are 2 to 9. It's here, but it's not from a sample that was selected at 1996. It's actually these people who are 2 years older. You pick the ones that are, you pick those that are now 2 to 9 at this point. Cycle 3, 1998. Again, we have information about people who are 2 to 9, but now it's coming from, again, the original cohort and from these, this cohort, which actually wasn't chosen at this time point. It was chosen here. And the same here. We've got 2 to 9s. We now have data from 3 different cohorts making up the sample of people that are 2 to 9. So now if you go on to the data file, if you go on to the data file for 1996, 1998, 2000, and 1994, well, let's take these 3. You do have a cross-sectional weight. So you could use that cross-sectional weight, and you're probably going to have estimates that are pretty close to being cross-sectionally representative, because the people who are 2 to 9 from the original cohort are probably pretty close to the people who were 2 to 9 if you'd actually picked them from this sample. And you probably wouldn't have too much difficulty here, and maybe not even here. And this cross-sectional weight has been chosen so that it's as close as we could make them look like a sample that was actually drawn from that time point as we could. So let's go back here. Okay, so as I said, here's what we've actually got. We used the original cohort, but just the 2 to 9-year-olds. The original cohort, but 2 to 9 at cycle 2, and now we've actually got 3 different of our cohorts included here. So, as I said before, the use of the cross-sectional weight at each time point should give a pretty reasonable estimate for that time point. And you could also use the corresponding cross-sectional bootstrap weight. So you get a variance estimate that's pretty good for that time-specific point estimate. Now, we realized that analysts, even if we've got these, what shall we say, longitudinal individuals being used for a cross-sectional purpose, it was soon recognized that analysts are probably going to want to do comparisons across these cross-sectional time points. And that means if we've used longitudinal individuals, which means they actually fall in more than one of these time points, our samples aren't independent. And that's going to cause some problems. So they actually, this initially came up for the first time when the National Population Health Survey started. And the methodologists created the weights for cycle 1, and then they had cycle 2, and they created weights and bootstrap weights in the usual manner. And then someone said, we want to compare those 2 time points, and we don't think those bootstrap weights have been created correctly for us to actually pick up the covariance. So there was some research done, and we came across with a way that actually we could use to still come up with bootstrap weights that would account for this dependence. And what we've called them are coordinated bootstrap. And what's actually been done is we know ahead of time we want to use these longitudinal individuals for cross-sectional purpose. So in the construction of the coordinated bootstrap weights, the sample of PSUs from each stratum for each bootstrap weight. That's what we do. For a bootstrap sample, what we take is a sample of primary sampling units within each stratum. So what we do is the sample of PSUs from each stratum for each bootstrap weight is selected at the very first time point that a cohort can be used for cross-sectional purposes. So we pick 500 of those, say. And then we use those same PSUs over time for every time that cohort is used for cross-sectional purposes. So every time we produce a cross-sectional weight that uses that particular cohort. So there's a little bit more work in creating these bootstrap weights. Well, I think one of the questions that I think and what came to me was, gee, it doesn't look as if people have to do anything to make sure that they're taking account of this would you say covariance amongst the samples when they're doing this cross-sectional analysis and getting variance estimates. Well, actually, an analyst has to do one thing. Like, if he's actually using the cross-sectional bootstrap weights for estimating variances of something that from two different time points, he has to make sure that he lines them up properly, which is not the case in most times when you're using bootstrap weights. So what you have to do is you have to line up your bootstrap weights of the same number over the different time points. So, I think if any of you have pooled data, we say, okay, you can probably bring the observations from one cycle and their bootstrap weights, observations from another cycle and their bootstrap weights. And really, it doesn't matter what order you have those bootstrap weights in. Usually it doesn't. It does matter for the cross-sectional. So you make sure you have bootstrap weight number 1 lined up with bootstrap weight number 1 from the other cross-sectional sample. And that's the work that the analyst has to do in this situation. So, like, here's a little example. Suppose we want to estimate the proportion of children in 1994 and 1996 who are hyperactive, and we want to use the cross-sectional weights. So we do that, and we get an estimate for this proportion. This is 1994 cross-sectional weight for that time point, 1996 cross-sectional weight for that time point. And then what we want to do is estimate the variance of this difference. So you know how we actually do things for bootstrap variance estimation. So what we do is we calculate this difference using bootstrap weight number 1 from each time point, and then we get the difference using bootstrap weight number 2, number 3, number 4, and then you'd combine these different estimates, how we usually do for bootstrap variance estimation. And the software does it for you, provided you line up your weights properly. So it's fairly straightforward for that particular situation. A lot of people say, I didn't do anything. Well, they probably did it without knowing that they did take account of this covariance because of the samples not being independent. So that was that particular question. The next question is a little bit more complicated, and this is when people are fitting marginal models to the data. And the question was, someone was fitting a marginal growth model to children when they're aged 4 to 9. I don't actually know what the dependent variable was here. But what they were doing is they were making the restriction, the children have to be in the initial NLSCY cohort, and the dependent variable that they want to model is only collected beginning in cycle 2. So it's in cycle 2, cycle 3, and so on. So now the question again is, how is the dependence in the observations accounted for in the model and when doing variance estimation? And what weight would you use when you're doing this analysis? So, okay, so let's go back again to this picture. So the analyst states that this is the cohort that they want to use for their analysis. So they only want to use this cohort. And we have data for that cohort over a lot of different years. If we go down now to this, I always find to sort some of this out, always a picture often makes things easier to see. Okay, so now I want to look at the observations from cohort 1. Like what would I have by age and cycle that satisfy the criteria that the analyst, the researchers is making. So remember in that initial cohort were children who were 0 to 11 in 1994 or 1994-95. Okay, so the ones that were 0 in 94 were 2 in 96, which is cycle 2, 4 in 98, 6 in 1000, and 8 in 2002, 10, 12, 14. Those that were 1 in 94 were 3 in 96, 5, 7, 9, and so on. And those who were 2 were 4 in the second cycle, 6 in the third cycle, 8 in the fourth cycle, and so on. So remember, what the person wanted to do was fit a growth model to children who were 4 to 9 years old, had to be in the first this first cohort, and we could only fit the model using data from cycle 2 onwards, because that was the variable. So we can see that anyone who was 0 in 1994 should have 3 observations that satisfy that criterion. So cycle 2 observation, or cycle 3 observation, 4, and cycle 5. Also, the people who were 1 in 94 would have 3 observations when they were 5, 7, and 9. Those who were 2 would have had, in 94, would have 3 observations, but it was in the second, the third, and the fourth cycle. Those are 3 the same. Now, those who were 4 in 1994 only would have had 2 possible observations, when they're 6 and when they're 8. After that, they're too old. And they're 6 in cycle 2, cycle 8, and those who were 5. Those who were 6 in 94 could only offer 1 observation, and those who were 7 in 94 would only have 1 observation. So these are the possibilities for getting data for fitting this model. Now, so let's look at the really simplest growth model, marginal growth model. So marginal models are considered to be longitudinal models in a way. So we could let I identify the person, J identify the year or the cycle, and a simple growth model for some variable Y, the mean for Y for the ith person at the jth time is a linear function of his age at that time point. So this is the very simplest that that the growth model could be. And often, if you've done much reading about marginal models, often people also specify the structure of the dependence amongst observations. So if you went into classical statistics, such if you look at a Liang and Ziegler, or Diggle, Liang, and Ziegler, when they specify the structure amongst observations, what they do is they consider people to be independent, and they put some sort of structure on the dependence among observations from the same person. So if you've read any of that, you've seen that this is what they do. And we probably would like to do something similar for our survey data. So, sorry, I'll go back. This structure that people put on the the covariance amongst observations. We often call that the working correlation. You're making your best guess at what it should be. So when you fit marginal models to longitudinal survey data, some software does allow you to specify a working covariance for observations from the same person. Now, Sudan, and if you've used Sudan for fitting these marginal models, they allow you to specify that that you've got independence amongst the observations for the same person, or there's an exchangeable covariance, which means the covariance is constant. Neither of those assumptions would be very good if what you're feeling is that the farther apart the observations are from the same person, the smaller should be the covariance. So they really don't offer you much. Sudan doesn't offer you much in options here. But what has been shown, like in the classic case, like if you read Diggle, Liang, and Ziegler, estimates of the model coefficients are approximately unbiased, even if the within-person covariance structure is wrongly specified. So that means that even if you say it's independent, your estimates are approximately unbiased. Even if you say it's exchangeable when it isn't, they're approximately unbiased. And so the same thing holds for survey data. And if you're using survey data and using a design-based approach, the between-person covariance, which we feel is not zero in surveys, well, that gets picked up through the design-based variance estimation, which is through our bootstrap weights for something like NLSCY. So you can use that software. Most cases, if I were fitting a marginal model using Sudan, I would choose independence as my choice, because the exchangeable isn't any better. If for most models you're really feeling that as within a person, if the observations are farther apart, the covariance should be less. That's not even offered in Sudan. So I have to go with the fact that things are approximately unbiased anyway. Okay, so go from there. But still, we've got the question: what weight variable would make sense when we do analysis with this longitudinal cohort? I think if you look at how people describe longitudinal weights, if you're following the same cohort over time, you know that as time goes on, people drop out. So what you do is over time, we've got the same population that's aging. That's what we're wanting to study by the longitudinal survey. But because of people dropping out, we've got a different subpopulation that represents the population each time. So here we start out with the biggest sample, but by cycle 2, it's going to be a little bit smaller, and by cycle 3, it's probably a little bit smaller yet, and so on. And what we do is we adjust the weights of those who do respond so that they can still represent this population as it ages. So we require the people that we actually do have responses from to pick up the slack from those who didn't, and so we adjust the weights based on whatever knowledge we have to try and make these people represent, do as good a job as the original sample, if these folks had actually responded at each time point. So we say for the NLSCY, for this particular example, we are using longitudinal data. So we've got some different options about what weight should we use. Now, sometimes people say, oh, you should use the weight of the final cycle from which you're actually using the data. Now, there are some pros and cons of that, because if you use the weight from the final cycle, it's 0 for anyone who didn't respond at that time point. So, but you're using data from several cycles before that. So if you use the weight from the final cycle and someone responded to all but the final cycle, you don't use their data at all in a longitudinal analysis because it's got a weight of 0. It drops out. So what could happen then is you get less efficient estimates than if you could use all the data. You've got fewer observations to work with. Another possibility is that this final weight could produce biased results if what you're studying is related to the dropout. I mean, we produce longitudinal weights making best use of the information we have and thinking, let's make the best weight that we can use or we can produce for a multiple of different uses. For your particular use, it may not be the best. It might actually produce some biased results. But we can't look at every situation when we're producing those longitudinal weights. Another possibility is you could use the weight of the first cycle. And we know that the weight from the first cycle is non-zero for everybody. So that means that for this type of situation, you would pick up any data from any person for any cycle that they responded in. But you're going to have some data that you should have had, but it's going to be missing due to the unit non-response. Well, again, that could cause some bias from what you would have if you actually had all the data from all the individuals. So there's often a trade-off as to which weight variable to use, and you often have to make a decision. Sometimes, if you've got the time, try it both ways. Try the different weights and see if it has an impact on your conclusions. It's one thing you could do. I want to go back to the picture just a second here. I can get this. Okay, this is kind of a funny situation. For many longitudinal analyses, you're using the same cycles of data from everybody. This is a funny situation where you're using cycle 2, 3, and 4 for some people, 3, 4, 5 for some people, 2, 3, 4 for others, just 2 and 3, or just 2. So this is odd in that the final cycle of data that we're using, it would be the 2002, but we don't even want data up to that time point for some of these people. So you can see if we use that weight, if this guy dropped out anywhere along here, his weight would be 0, so we'd miss this. So there's more opportunity in this sort of situation for us to lose data because of using the weight from this final cycle. Well, second, let's go back here. In this particular case, if you looked at the equations that we're using for estimating what we want, it can actually be broken into pieces where each piece involves a different cycle. So for repeated measures in these marginal models, we don't have to stick to the first weight or the last weight. We can actually use a different weight variable to estimate the different pieces of data. So use a one weight variable to estimate the piece of data that comes from cycle 2, another weight variable for cycle 3, cycle 4, cycle 5, and so on. It's one of the few situations where this actually holds true. So it's I don't know that many people have actually tried this or not. It would be worthwhile. I should get an example from someone and see what impact this actually has on how much data you have, and what the estimates are. So that's all I was going to do this afternoon on those 2 questions on NLSCY, because I knew you'd be getting tired. But I'd be happy to answer any other questions. Yeah.
To be sure about the last question.
Yes.
You recommend to use different weights.
Yes.
Different longitudinal weight at each cycle.
Well, what you do is, let's go back here. Okay, you know, when you set up your data for this particular situation, you're going to have 3 records for this person. A record from cycle 3, a record from cycle 4, and a record from cycle 5. So on each record you have to put a weight. So on the record that contains the variables for cycle 3, the information for cycle 3, put the cycle 3 weight as well. For this one, for the record for this, for when the chap was 6, put the cycle 4 weight. For this, the observation here, put the cycle 5 weight. So you actually will, and then say for this guy, if he has, who was 7 when he was chosen, and you only get 1 observation from him, put the cycle 2 weight on that observation. So the different records from the same person will actually have weights from different cycles. So, yeah, the longitudinal weight. Yeah.
And I'm not sure if I understand when you talk about Sudan. So you recommend to use the exchange working covariance structure? Not
it doesn't matter. It depends on what you're studying. Like if you're studying something where you really think that, say, okay, so you would think that 2 observations that are close together are more correlated than observations that are farther apart in time, say for a child. The exchangeable doesn't make sense, nor does the independence. So I don't even bother putting in the exchangeable, because if you put in the exchangeable option, it has to calculate this correlation over time, which is one more parameter it has to estimate. I wouldn't bother either or try the independence, which is sort of the default. Try the exchangeable. If you come up with different conclusions, start to think of why is that. There must be something going on there. So unfortunately, as I say, there aren't any other options offered in Sudan. So in the classic software, they often have more options for what that structure could be. And it seems as if your working assumptions on the covariance are closer to being true, your coefficients are probably going to be more efficient. We know they're approximately unbiased regardless of what you assume for the working covariance. But if you're closer to the truth, the coefficients are probably more efficient, have smaller variability.
And why is it so bad to use the procedure and SAS and do a bootstrap macro with it?
Well, prop mixed, you're now getting into multi-level modeling. A marginal model is not a multi-level model. This was not a. This is.
It's close to. It's not too close.
Well,
to
you
that.
see, actually.
Because you have subject and time, so you.
Yeah. Now, if you went to a multi-level model, what you'd probably do is say you'd have your model would say the intercept varies with the person. The slope varies with the person, so it'd be alpha I plus beta I times age. And then you might model each alpha I and each beta I as some function. But in a marginal model, you're making the assumption right from the start that this is fixed and this is fixed. It's called a mean population model. Yeah, but a lot of people would, for growth models, would prefer to go to multi-level models. And then proc mix doesn't correctly calculate variances. That's what. Yeah.
So it's more appropriate in some low marginal model.
Yeah. Well, if that's what seems to make sense for you. Yeah. Okay. Any more questions? Yeah.
Pull all the waves together, or pull all the cycles together, and for the width we are using. So I think you just said that, and if we use the first wave, the width from the first cycle or the last cycle, it would be biased. So that means that if I combine some of them together, so is it a better strategy, or is it the common rule for all the longitude data? If I combine the different cycles together, I use the earliest wave that I combine it. The earliest width from the cycle I used. For
the survey that you're using, that longitudinal survey of immigrants to Canada.
Yes.
Actually, the weight. What should I say? The target population for that survey when it started was all immigrants to Canada within a certain time period. Was it over a year? By the time it got to the wave 3, the target population for the survey hadn't changed, but the weights were actually created for a subpopulation, which was those people who immigrated to Canada within that time period and also stayed at least 4 years. So it doesn't even represent the same population as do the weights if you looked at wave 1 of that survey. It has some differences from a lot of our other surveys where we have different weights on the different cycles of a longitudinal survey, and why we have different weights is because we're trying to account for the non-response, but we still have the same population in mind. In that one, they actually changed the population that they had in mind. It's a subpopulation of the original one. So it's a different, it's slightly different.
Okay.
Yeah.
Thanks.
Yeah. But say if you were going to, at wave 2, I think they were still considering the same target population. So if you were just going to use data from wave 1 and wave 2, you'd have to think, should I use the wave 1 weight or should I use the wave 2 weight? And I think for that survey, the percentage of non-response was so high at the second time, it probably would be a good idea to use the wave 2 weight, because I think they did a fair amount of study about why people had not responded and incorporated that into the weight adjustments. So it might be a better choice in that situation. Yeah. Okay. Well, thank you very much. I enjoyed coming today. Yeah.